Recording in progress.
Okay, share screen, see whether it's okay.
Okay, for it.
See your face, okay? This is the camera. You must use the microphone. Okay. Oh, it's a bit annoying, but you have to admit these people.
Oh, I see.
Yeah. Periodically, when these people will stream in. Okay, please take attendance. Today we're going to give our students a chance for the first 1 hour. What? Oh, wrong class. This is my other class. This one. Sorry. Sorry. I just want to remind people. I'll repeat this for easy people. Has everyone submitted the homework? Only before midnight, okay? Has everyone here taken attendance? Okay, good. Even though it's my student, feel free to ask questions, okay? In fact, ask more. sentence anew, it will come up. Okay. It's present. Okay. Good.
everyone hear me? If anyone can hear me, please type something on the chat. Okay, thank you. Hello, everyone. This is my first time giving a lecture, so I'm Vincent's PhD student. Today, I will cover section 1.6 of Gallager's book. So this section mainly includes 3 parts. The first is Markov's inequality, the second is Chebyshev's inequality, and the third is Chernoff bounds. So first, let's start with the Markov's inequality. So Markov's inequality states that let y be a non-negative random variable with mean of expectation of y. Then for any positive value y, the probability of y greater than this positive value y is smaller than the expectation of y over y. So this is called Markov's inequality. And we need to pay attention that y must be a non-negative random variable here, and y must be a positive value. So how can we better understand the Markov's inequality? We can actually...
There are 2 people there.
Oh, sorry. Yeah, so how can we better understand the Markov's inequality? We can first draw a picture of the complementary CDF of y. So complementary CDF, that is 1 minus the CDF of y. This is the complementary CDF of y. And let's draw a picture of it. So let the horizontal axis be z and the vertical axis be y, the probability of y greater than z. Let's assume that this curve looks like this. So at the 0 point, this is equal to 1. And this is the complementary CDF of the random variable y. Then under this curve, this is the area under this curve. We can calculate it by integrating the probability of y greater than z. From 0 to infinity, let's integrate this. And this is actually equal to the expectation of y. Why this is equal to the expectation of y? Actually, we have mentioned this in last lecture, in lecture 2. This is called effects of layer cake representation. So you can go back to check the lecture 2 notes to find why this is equal to the expectation of y. And then let's fix some value, positive value y here. So the corresponding probability of y greater than y is here. Then we have this rectangle. The area of this rectangle is actually equal to the width times the height. So this is equal to y times the probability of y greater than y. Then obviously we can see that the area of this rectangle must be smaller than the whole area under the curve. So we have that the probability of y greater than y times y is smaller than the expectation of y. So this is the Markov's inequality. This is a quite intuitive explanation to understand it. And from this picture, from this figure, we can also see that if y goes to infinity, this rectangle will be very, very short and very, very fat. And as y tends to infinity, it will go to the area of this rectangle will almost be 0. So we have this limitation here. When y goes to infinity, this is equal to 0 if the expectation of y exists. So any problem here? Okay. Then let's give an example of use the Markov inequality. Assume that y represents the height of a random student in the class. And then let's say that the expectation of y is 1.6 meter in the class. Then what's the chance that y exceeds 1.5 times the expectation of y? So if we apply Markov inequality here, we have this result. This can be upper bounded by 1.5 times expected of y over, the expectation of y over 1.5 times expectation of y. So this is equal to 2 over 3. However, we can see that if the expectation of y is equal to 1.6, then 1.5 times the expectation of y is equal to, this is equal to 2.4 meter. But in reality, the probability that a random student is higher than 2.4 meters is actually very, very low. So this bound here is actually quite loose. So in general, the Markov inequality may be quite loose under some cases. Oh, okay. However, there do exist some cases that Markov inequality is very tight. This is another example. Let's say x is a random variable that either equals to 0 or equals to 5. We assume that the probability of x equal to 0 is 24 over 25. And the probability of x equal to 5 is equal to 1 over 25. Then under this case, the expected value of y is equal to 1 over 25 times 5, so it's 1 over 5. Then what's the chance that x exceeds 5? So the probability of x exceeds 5 can still be upper bounded by expected value of x over 5. And this, is equal to 1 over 25. And we can see that this is also the probability of x exactly equal to 5. So this bound is tight under this situation. So we can see that when in the situations when no better bound can be achieved using only the expectation of x, then the Markov inequality is quite tight. So here are two examples that shows the cases when Markov inequality is tight and is loose. So next, let's prove the Markov inequality mathematically. First, we have the fact that the indicator of y greater than y can be upper bounded by y over y for all y greater than 0. Why this inequality holds, we can see that if y is greater than y, then y over small y is greater than 1, which is exactly equal to the indicator of y greater than y. So on the other hand, if y is smaller than y, then y over y is greater than 0, which is equal to the indicator of y greater than y. So this is why this fact holds. And then we can take expectations. We can take expectations on both sides of the inequality. So we get and we notice that this expectation of the indicator of y greater than y is actually equal to the probability of y greater than y. So the Markov's inequality is proved. Any question here? Okay. Then let's move to Chebyshev's inequality. Chebyshev's inequality says that if z is a random variable with finite mean Ez and finite variance, sigma z square, then the probability of z minus the expected value of z square greater than y can be upper bounded by sigma z square over y for all y positive. So here we need to notice that z must be a random variable with finite mean and finite variance. However, actually the finite variance implies the random variable has finite mean. And we don't require the z to be a non-negative random variable. It can be negative here. So we might wonder, what's the difference between the Chebyshev's inequality and the Markov's inequality? Chebyshev's inequality here applies to random variable with finite mean and variance. Finite mean is actually the first moment of the random variable, and variance is a combination of the first moment and the second moment. So Chebyshev's mainly makes use of first and second moments. However, the Markov's inequality applies to non-negative random variable with finite mean, but the variance can be infinity. So Markov's inequality only makes use of the first moment. And this somehow shows that the more moments we use, the tighter the results we can get in general. Yeah. So in general, Chebyshev's inequality may be tighter than the Markov's inequality since it makes use of more information and have more assumptions. And we can also we can make use of the Chebyshev's inequality to answer the following question. What's the probability that Z deviates from EZ more than C times sigma square, sigma Z for some C greater than 0? So let's write down the probability of Z deviates from EZ greater than C times sigma Z. And then we can take the square on both sides. So that we can apply the Chebyshev's inequality here. And this is equal to less than 1 over C squared. So yeah. So this two inequality is almost the same, but personally, I think most of the cases we use this kind of form to solve the problem. So next, I will go to the proof of the Chebyshev's inequality. The proof of the Chebyshev's inequality is quite simple. We can simply apply the Markov's inequality. To the non-negative random variable Z minus EZ squared. So this is a non-negative random variable, so we can apply the Markov's inequality to bound this probability by taking the expectation of it and over Y. So the numerator is equal to the variance of Z. And this is sigma Z squared over Y. So the Chebyshev's inequality is proved. Yeah. So next we will go to the Chernoff bounds. Chernoff bounds is in general a tighter bound than the Chebyshev's and Markov's inequality. So it must assume more, must have more assumptions than the previous two inequalities. So first, let's begin with an example. Let x1, x2, xn be IID Bernoulli random variable, where the probability of xi equal to 1 is p, and the probability of xi equal to 0 is 1 minus p equal to q. If we fix any epsilon greater than 0, then the probability of the absolute value of the empirical mean minus p greater than epsilon. We want to bound this probability. So p here is actually equal to the expected value of x. So since both sides are positive, we can simply take the square. Yeah, so since this term is non-negative, we can directly apply the Markov's inequality, and we have that it is upper bounded by the expectation of this term here over epsilon square. Here we apply Markov's inequality. And then we can further expand this whole expectation term. So we get that expectation of x plus p squared over epsilon squared here. So, and all this can be exactly calculated, and we get that this bound is actually equal to p minus p squared over n times epsilon squared. So if we let p equal to q equal to 1 over 2 and take epsilon equal to 0.01, then this upper bound, this probability, if we want this probability to be smaller than 0.01, so we can plug this into here, and we get that we need at least 250,000 samples to achieve this bound, to make this bound can be upper bounded by 0.01 by simply plugging this into here. So, however, in reality, do we really need such a huge amount of samples to get this upper bound for the probability? Actually, there are two cases. So the first case is that, yes, we need such a huge amount of samples to get this upper bound if further moments don't exist for this random variable. And no, if more moments exist. So for this Bernoulli random variable, actually all moments of Bernoulli random variable exist. So this bound here, must be very loose for this by applying the Markov's inequality. Then we want to introduce the Chernoff bounds. So before that, we need to define the moment generation function of a random variable x. The moment generation function we denote it as gxr, which is equal to the expectation of e to the power of rx for r real value. We assume that the moment generation function of x exists for all r in the neighborhood of 0. What's the neighborhood of 0? That is this is called the neighborhood of 0. So why do we want the moment generation function exist in the neighborhood of the 0? That's because we can differentiate it in the neighborhood of 0 so that we can get the moments of the random variable. know that at 0 point, gx0 is equal to 1. And the first derivative of the moment generation function at the is equal to expectation of x times e to the power of rx. And the second derivative of the gxr is equal to expectation of x squared times e to the power of rx. And the kth moment, or the kth derivative of the moment generation function is equal to the expectation of k to the power of x to the power of k times e to the power of rx. So we can see that if we take r equal to 0, then we exactly get the moments of the random variable x. So this is the kth moment of the random variable x by taking the kth derivative of moment generation function and taking r to be 0. So the existence of moment generating function gxr actually implies the existence of the moments of x. Any question here? Yeah, then let's continue. So for any random variable z, we can apply Markov's inequality to get the probability of e to the power of rz greater than some positive value y is upper bounded by the expectation of e to the, sorry, it is not quite clear. The expectation of e to the power of rz over y. And the numerator is the moment generating function of z. Oh, sorry. Here we can apply the Markov's inequality since this is greater than 0. This is a non-negative value. So then we replace y by e to the power of rb for some real value b. So we replace this to here. And then we get the probability of e to the power of rz greater than the e to the power of rb can be upper bounded by for all r greater than 0 here. So this is simply by plugging this bound here. And since we assume that r is a positive value, so that this probability is equal to the probability of z greater than b. So now we have an upper bound for the probability of z greater than b, which is an exponential bound here. Then in the other direction, for all r smaller than 0, we want to obtain the bound for the probability of z smaller than b. Since r is negative, so if we multiply r on both sides, then this will be the other side. So we have this. So this probability of z smaller than b is equal to the probability of e to the power of rz greater than e to the power of rb. And we can also simply apply this bound here to get that the exponential minus rb times the moment generating function of gz. This is for all r smaller than 0. So now we can go back to the original problem we just proposed. Fix any r greater than 0, the probability of the empirical mean of xi greater than epsilon. Here we consider xi's are ID random variable with expectation equal to 0 and the moment generating function exists. So previously we considered the absolute value to be greater than epsilon. So this is so here this is a one-sided version of it. We can further rewrite it as the probability of the sum of xi greater than n times epsilon by multiplying n on both sides. And since r is a positive value here, so we can multiply r on both sides without changing the direction. And then we can take exponential on both sides. So this probability is equal to the exponential r times the sum of xi greater than the exponential r times n and epsilon. And then we can also apply the Markov inequality here. So this is equal to expectation of the exponential of the sum of xi. Yeah. Since xi's are ID random variables, so this expectation is actually equal to the exponential rx to the power of n. Does anyone have question on this?
Second last one should be inequality.
Oh, yeah, this should be inequality, sorry. So, yeah. Anyone has question about this equality here? Yeah, so if we don't have an equality, we can just replace this expectation to the moment generation function gxr. So now we can see that by using the moment generating function, we have a bound that looks like an exponential bound, which seems to be tighter than the previous bounds derived by Chebyshev's inequality and the Markov's inequality. But we need to further solve the moment generating function here. So let's define a new notation. The semi-invariant moment generating function. We also call it cumulant generating function. So we define it to be gamma xr by taking log of the moment generating function. So that we can plug this gamma xr to here. And then the probability can be rewritten as so this bound, we can see that this is exponential in n. For fixed epsilon and fixed r. And we notice that this term is actually, for any fixed epsilon, this term is actually a function of r. So if we want to get a tighter bound, we can further minimize this exponent over r. To obtain the smallest upper bound. We minimize gamma xr minus r epsilon over all r greater than 0. That is this exponent here. So know that when r is equal to 0, gamma xr minus r epsilon is equal to 0. And then if we calculate the first derivative of gamma xr minus r epsilon and taking r equal to 0, this is actually equal to the expectation of x minus epsilon. And previously we assumed that the expectation of x is equal to 0. So this is minus epsilon, which is less than 0. So it means that at the point when r equal to 0, the curve of gamma xr minus r epsilon is decreasing. So this means that gamma xr minus r epsilon must be negative for sufficiently small r. Let's draw a picture to see how it works. Yeah. So let this be r, and let the vertical axis to be gamma x minus r epsilon. So first we know that at the 0 point, the value is equal to r here. And we know that at the 0 point, the slope is equal to minus epsilon, so it's negative. So it's decreasing. The curve here is decreasing in this direction. So this curve may look like this, or it may look like this. So how it looks like, it depends on the second derivatives of this function. So first we know that r minus r epsilon equal to 0 is 0. And then the first derivative is smaller than 0. We can further calculate the second derivative at the point 0. This is equal to the variance of x, which is positive. So since the second derivative is positive, so this curve must look like this. Sorry. Yeah, this curve must look like this. Since the first derivative is increasing, so the curve will be like this. So we can see that at this, for r greater than 0, at this region, the function gamma x r minus r epsilon is negative. This curve is under the 0 axis. So we can say that gamma x r minus r epsilon must be negative for sufficiently small r. Any question here? Yeah, since this function is negative for sufficiently small r, then we can say that this exponential term is decreasing in n, since the exponent is negative. So we can say that, so we know that this decreasing exponentially in n must be faster than the, say that this is the exponentially decreasing curve, and this is a curve of 1 over n. So this one is faster than this one. So we conclude this to be the Chernoff bounds. Let xi be IID random variable, and let Sn be sum of x1 to xn. Assume the moment generating function gxr exists for all r in real region. Yeah. Then the probability of the sum of x1 to xn greater than n multiplies epsilon can be upper bounded by exponential n times mu x epsilon. Mu x epsilon is equal to the infimum of gamma x r minus r epsilon over all r greater than 0. Furthermore, mu x epsilon is smaller than 0 for epsilon greater than the expectation of x. And mu x epsilon is equal to 0 for epsilon smaller or equal to the expectation of x. So why do we have this result? we can see that the first derivative of gamma x minus Rx is equal to expectation of x minus epsilon. So if epsilon is smaller than, oh, sorry. Yeah. Wait a minute. I think, sorry. I think I write in the wrong of, sorry. This should be epsilon less than. Yeah. So if epsilon is smaller than expectation of x, then this is positive. If the first derivative is positive, then this curve will not look like this. It will somehow looks like this. So the value, so gamma x r minus r epsilon will be positive. Oh, so yeah, will be positive for r greater than 0. So by taking infimum of this function, the infimum of the function is equal to 0. So mu x is equal to 0. Mu x is the infimum of gamma x r minus r epsilon.
Does it say that for epsilon lesser than your expectation,
Yeah.
basically don't get a bound anymore? You plug it in, right? It's just probability that it's greater than equal to n epsilon. It's just less than equal to 1. It's just trivial norm.
Oh yeah, if this is equal to 0, then this is just a trivial bound. Yeah.
Another question I had is that the justification for why your gamma x is less than 0. You argue that the derivative is negative, right?
Yeah.
It's not sufficient if the derivative is only negative at that particular point. There are pathological functions where even though the derivative is say negative at that point, it's not necessarily decreasing at that point either. It needs to be negative over an interval or continuously differentiable and negative.
Let me see. Since the second derivative of this function at this 0 point is positive, so let me see. I think if we take the derivative of this function let me see, the derivative of xr minus e is equal to 2xr times. So if
maybe I can answer this because we indeed have continuous differentiability. This function is not so pathological. We have continuous differentiability because the second derivative also exists. So the first derivative is certainly continuous. So the function gamma x r minus r epsilon is certainly decreasing near 0 to the slightly right hand side of 0. So the minimum is definitely negative.
Yeah. Any other questions about this theorem? So let's compare the Chernoff bounds with Markov's inequality and Chebyshev's inequality. So obviously the main difference here is the Chernoff bounds make use of all moments. All moments since we assume the moment generating function gxr exists. So by Taylor expansion here, the moment generating function is actually sum of the moments. So if the moment generating function exists, then all the moments from 0 to infinity exist. So it shows that if we make use of more moments, we can derive tighter bounds by comparing these three inequalities.
Does that also mean that Chernoff bound is the tightest you can get?
I think this is just for this probability. This is the just for this probability.
Maybe I can answer this question. So in my notes, I show that this is the tightest you can get. This is the tightest you can get in some sense, in the asymptotic sense. So here the upper bound here holds for all n, running from 1 to 2 to 3 to 4. Okay, but if we consider the asymptotics, alright, then actually you cannot improve on the exponent u x epsilon. That is what H1 and 2 of my lecture 3 notes. But the lower bound is my current.
Yeah. Okay. So with the Chernoff bounds, let's go back to the original problem we proposed at the beginning. That is, if x is a binary random variable and the probability of s equal to 1 is p, the probability of x equal to 0 is 1 minus p equal to q. So we can derive the moment generating function of the Bernoulli random variable x to be q plus p times e to the power of r for all real value r. Then the cumulant generating function is just taking the log here. So we want to derive the bound for the probability of the sum of x1 to xn greater than n times p plus epsilon. This is equal to the empirical mean of xi greater than p plus epsilon. So this is, so at the beginning we consider the probability of empirical mean minus p greater than epsilon. So this is a one-sided version of the problem we considered at the beginning. And according to the Chernoff bounds, so this probability can be upper bounded by exponential mu x plus epsilon. So notice that this is p plus epsilon since we want it to be greater than n times p plus epsilon. So, and the mu x p plus epsilon is taking infimum of gamma x r minus r times p plus epsilon here for all r greater than 0. And if we put this moment cumulant generating function here, so we can get then to derive the infimum of this function, we can simply by calculating the derivatives and taking it to 0. So differentiation. The optimal R we can obtain is equal to P log P plus epsilon times 1 minus P over 1 minus P minus epsilon times P. So this can achieve the infimum of this function over R. For epsilon greater than 0, this R is greater than 0 since we are taking infimum over all R positive. So it's also achieving the minimum over R. Then by plugging the R star back to mu x plus epsilon, we can get this equation. So this equation, this expression here is commonly known as the minus KL divergence between the two probability distribution P plus epsilon and P. KL divergence is an information theoretic quantity that is commonly used and is defined as this. So and it's all known that KL divergence between two distributions is positive. So this minus KL divergence is negative here. So that means that the mu x P plus epsilon is negative. Then the probability of greater than P plus epsilon can be by plugging this back to here, we can get the exponential minus n times the KL divergence between the two probability distribution. So this exponential term is definitely decreasing in n. And if we want this probability to be less than 0.005, which is tighter than the example we gave previously, and epsilon equal to 0.01, and let P and Q equal to 1/2. So since Bernoulli random variable has all moment all moments. So we can apply the Chernoff bounds here. So to achieve this probability bound, we need at least at least 263 samples. So recall that if we use the Markov's inequality and we want the prop to be less than 0.01, we need 250,000 samples. So this is much smaller than the 250,000 samples. So that we can see that for the random variables that have all moments exist, applying the Chernoff bounds can achieve very tight results. So any questions so far? If there is no further question, then my part is finished. Yeah, thank you very much.
Good. Now let's take a 15-minute break. We all come back at 7:17, okay? Yeah. Very good. Stop. Okay, I just want to remind people that you have to turn in homework 2 by tonight. And tomorrow I'll release the solutions to homework 2 and homework 3. Hopefully I finish typing by tonight. Okay. So we will have a quiz next Friday from 8 to 9 p.m. We have the usual lecture from 6 to about 7:45. Then you'll take a break. Then 8 to 9. Do you want more time or not? Do you want more time until 9:30? Because I think the quiz is pretty long. I got very creative with questions and then I decided to put more and more in. But then it means that you have to stay here longer. Okay. But okay, maybe I can give you up to 9:30. We are always flexible. All right. In terms of what you can bring, right? You can bring one piece of handwritten notes on both sides. So you get one A4 paper. All right. And you can write anything you want on both sides. Maybe I'll ask you to write on paper. Okay. I will provide paper for you to write on. I will print the question paper as well. Okay. So everyone, apart from those people who told me that they cannot make it, must come to LT1 to take the quiz if you want to take this class for credit. Okay. I think these instructions are clear. Any questions? Any questions from the Zoom people? Yes. Okay. It's problem sets 1 to 3. All the probability, chapter 1. Understood? Clear? You can look at the past year quizzes, is all there. I can tell you, one question is on conditional expectation. I already said this last lecture. One question is on the example that my student did just now on the Bernoulli distribution and the large deviations, the Chernoff bound for Bernoulli distributions. One question will be on that. And one question will be on convergence of random variables, which I'm going to talk about now. Very clear, right? Yeah. Okay.
All right, so in case you have any questions, you can come and ask me. We will also have office hours next Thursday as usual. So this is section 1.7 of the book. When I say this is section 1.7 of the book, I mean you will read section 1.7 of the book, in addition to listening to me talk, of course. Just now, my student talked about everything in section 1.6, okay? Okay, so here we are going to talk about convergence of random variables through different laws of large numbers, okay? So before I can talk about convergence of random variables, I need to remind you of convergence of numbers, all right? So let Bi be, okay, let's do this, be a sequence of real numbers. Okay, then we say that, okay, you will often see Bi converges to B. What does this mean? This means that, okay, let me make this a bit clearer. As I tends to infinity, this is a standard analysis type of thing. If and only if, for every small little epsilon I choose, I can pick a big enough number, n0, that depends on epsilon. This is an integer, such that what? Bi minus its limit is smaller than epsilon for every n bigger than n0 epsilon. Okay. Now, so this is the standard meaning of convergence of a sequence of numbers. For example, if I have Bi be equal to 1 over I, intuitively, this sequence of numbers is 1 over 1, 1 over 2, 1 over 3, da 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 da. All right. So intuitively, Bi tends to 0. So for those who have taken some sort of a formal analysis class, this should be obviously true to you that it goes towards 0. But if not, let us see. Let us verify this particular statement here. Okay. So you choose. Okay. Now you choose your favorite small epsilon. Say you choose epsilon equals to 10 to the minus 6. Now, can I find an integer, big enough integer, such that this sort of statement holds? Okay. The claimed limit is 0. Okay, this is the claimed limit. All right. So I claim that if I choose n0 epsilon equals to 10 to the 6 plus 1, that should be big enough. Then what happens here is that Bi is a 1 over I. Well, is it smaller than the prescribed epsilon 10 to the minus 6? Yeah, it should be. So if all, for all I bigger than n0 epsilon, typo here, no one told me, this is I, all right? For all I bigger than 10 to the power 6 plus 1, certainly this will be true. All right. We need the plus 1 because of how I define the limit, but it's a minor issue. So roughly speaking, if you look at the picture, all right, you have this sequence here, all right. And if the limit is equal to 0, what you are saying is, oh, I'm going to find this window here. This window is of width 2 epsilon. All right, and my sequence here goes here. Eventually, it may jump outside. This sequence here may jump outside here, but eventually there comes a point when, after this particular point, the sequence must lie inside this tube of width 2 epsilon. Okay, sorry, I'm trying to make this look nice. So this tube is a width 2 epsilon, okay? After a certain point, n0 epsilon, then the sequence, this is the Bi sequence, must be trapped inside the tube, okay? Must be trapped inside the tube of width 2 epsilon. This is nothing but convergence of numbers, okay? I told you, okay? So this sort of things, hopefully you have been exposed before. If not, then you need to put in a little bit of effort to come up with the intuition about these sort of things. But now we have learned how to walk. We are going to learn how to fly, because we want to talk about convergence of random variables, right? Convergence of random variables is significantly more challenging than convergence of numbers. Numbers, okay, this is the definition. Because recall that random variables, say xn, are functions from the sample space omega to r, i.e. it looks like this. Say xn omega, for every omega, so xn is a function, it takes in an omega, which is an element of the sample space, and it spits out a certain number. So this is like this, right? This is called a real valued random variable. So now this is no longer a number, because for every omega, you got a different number. You can talk about, okay, for I fix this omega, if I fix this omega, this is a sequence of numbers. All right, if I fix this omega to be omega 0, then this is a sequence of numbers. I can go to this sort of definition. But now I have this entire collection of numbers that is indexed by omega. How do we talk about convergence of this sequence of functions? We need something more sophisticated. All right. So there are many different modes of convergences for random variables. And this is the sort of message that this part of the course is trying to convey, that sequence of random variables converging is not as simple as sequence of numbers, because these are functions. Okay. Now, what did I just say? Recall that random variables are functions from a sample space to R. Hence, there are many ways a sequence of random variables, xn, we write this sequence like that, xn can converge to a limiting random variable. Okay, so there are many ways. So let's look at some of the ways. Today we will introduce weak law of large numbers, strong law of large numbers, and several other things. Okay, now this is a very short time that I have to talk about all this deep stuff. All right, but we will only need to know a little bit of this deep stuff for the remainder of the course. So I require you to know some definitions, and I require you to know how to do some calculations. You will have to do some calculations in the subsequent assessments, okay? So the first thing we will talk about is weak law. This is probably the easiest to talk about. Weak law of large numbers. Okay? So what is the motivation here? I have a coin. Just now my student Hai Yun talked about a coin. I go and toss the coin. The coin has a bias of P. The probability of heads is P. You toss the coin 1,000 times. 1,000 times. The fraction of times it comes out head should be around P, right? Otherwise, there's some strange phenomenon that is happening. Either you are very lucky or you are very unlucky. So if you are in the typical scenario, the fraction of times that you see the head is around P, 70%, if the bias of the coin is 70%. How do we make this precise? Okay? How do we make this intuition precise that if I toss the coin many times, the fraction of times that I see heads is around the bias of the coin? Okay, so theorem goes as follows. Okay, for all n bigger than or equal to 1, let Sn be the sum of the first n IID random variables of n IID random variables, each with finite variance, say sigma squared less than infinity. Then for all epsilon bigger than 0, so this is our threshold, limit n tends to infinity of the probability that 1 over n Sn, so that is the empirical average. There's a term for this. Empirical average minus the population average. This has a name. Statisticians like to call this population and empirical. This is the population, this is the empirical. Empirical is what you observe, the fraction of times that your coin turns out heads. That is 1 over n as n, right? Population is the ground truth, the bias of your coin. So the chance that it deviates by more than epsilon is equal to 0 as n becomes large. Okay? So that's the weak law of large numbers. The weak law of large numbers, the way I have stated it, requires finite variance only. No need for the moment generating function to exist. The way I state it, in Gallager's book, one of the exercises that I didn't ask you to do, this can be relaxed to infinite variance. Variance does not have to exist. The mean has to exist. All right, otherwise this you cannot even talk about this object here, right? Then how you talk about the weak law? You need at least the mean to exist. The finite variance, no need. But for this simple proof that we are going to do, having the finiteness of the variance is going to simplify our life significantly. Okay? But in one of the exercises that I didn't ask you to do, we can relax this assumption. So in other words, the empirical mean, the empirical average, 1 over n Sn, we say that empirical mean converges in probability. Later on, we are going to make this term precise to the population mean. We write this English statement as 1 over n Sn is equal to 1 over n sum ni running from 1 to n xi converges in probability to the expectation. Okay, we put this converge with a p on top. Okay, sometimes if you are very pedantic, you can also write this, okay, but never mind. Okay, so this says the following, very simple. You have a sequence of IID random variables, finite variance implies finite mean. Oh, just now my student said, finite variance implies finite mean. Exercise. Prove that if the variance is finite, it implies that the mean is finite. Okay, exercise. This is true. Okay, proof. Okay, so now we are not going to prove this simple thing, okay, but you should do it. We are going to prove the weak law of large numbers assuming finite variance. This is called the, by the way, this is called the weak law of large numbers, assuming finite variance. Okay, but I hope that everyone understands the statement. The statement says that, okay, if I toss a coin many times, then the fraction of times I'm going to see heads is going to be very close to the population fraction. The population fraction is this one, the expectation here. Okay, so basically the same picture holds, right? Here, suppose this is the population. If I toss many times, it must be inside here. Okay. Right, so let's prove this formally. This is going to be done by Chebyshev's inequality. By Chebyshev's inequality, how to spell Chebyshev? Oh, no Y here. That's why it doesn't look natural to me. By Chebyshev's inequality, let's control 1 over n sum xi, that is the Sn, minus the expectation value of x, deviating by more than epsilon. How to do this? Okay. So I did this very quickly here. So what does it say here? Okay, so let's do this slowly. This is equal to this square. So now we can, okay, everything here is non-negative. We can apply, I mean, by non-negative, this is a non-negative random variable. Actually, my student Hayun already did this calculation just now, but I'm going to do it one more time for you. This is the expectation value of 1 over n squared sum over I running from 1 to n of xi minus expectation value of x, quantity squared over epsilon squared. Okay, so basically we have, this is just application of Markov inequality. We can expand the on top. Okay, so we have basically, okay, I'm going to do it a slow motion way. N squared epsilon squared. So we have expectation value sum over I running from 1 to n of expectation value of xi squared minus 2 times of expectation value. Okay, I'm going to get this wrong. One moment. I did it very quickly here. The above would be n times sigma squared, okay, eventually. And then we will have n squared epsilon squared here. So we have to convince ourselves that the top is related to n times of the variance without this factor here. This factor here I pull down here. So this is equal to sigma squared over n epsilon squared. There's one cancellation, okay? So, right, so, okay. How we see this? Now, this is a zero, oh shucks. This is a zero mean random variable. Okay, this is because I've taken away the mean. Okay, so for a zero, the way to see this is the following. Expectation value of this. Now I can just write this. I don't want to have the, okay, expectation value of this xi minus expectation value of x all squared. The inside here is the argument here is a zero mean random variable because I've already taken away the mean. Right? So this is nothing but the variance. For a zero mean random variable, the second moment is equal to the variance. Okay? So it's the variance of this guy here. All right? I take is the variance, because for a zero mean random variable, variance of y is equal to expectation value of y squared. Y zero mean. Okay? Small little fact. So here, variance, all these guys here, all these guys and girls here are independent. So now I can bring this sum outside. I think this is one of the exercises that you did in the homework. So variance of xi minus expectation of x, you can take away this guy. Taking away something from a variance that makes no difference. So this is n sigma squared, as shown. So the justification of this guy here is done here. Okay? So what do we prove here? What do we show here? So what we have shown is that the probability of the empirical minus the mean. Okay, so maybe I should do this. Deviating more than epsilon is less than sigma squared over n epsilon squared. Sigma is finite. So this entire thing is of the order 1 over n, which goes to 0 as desired. So here we have proved the weak law of large numbers assuming finite variance. All right. If you do not know what is this, fine. Okay. But this is a sequence of numbers that behaves as 1 over n. So it goes towards 0. Okay. So what this is saying is the following. Any questions here with regard to this calculation? First, I apply Chebyshev's or Markov's inequality. They are approximately the same, so I will not belabor the point what is what. Okay. First, I apply Chebyshev's inequality. There should be this. Okay. Then this is basically, why can I do this? Because this left-hand side here is a positive or non-negative random variable. So we put it here. Now we can extract the 1 over n squared, put it here, and the epsilon, put it here. And the claim is that expectation value of this part is n sigma squared. Now this sort of thing you should know how to do. So now I calculate this one here, but this is a zero mean random variable. So for zero mean random variable, the variance is equal to the second moment. So I can do the variance of the stuff inside here, which is here. But everything inside is independent and in particular uncorrelated. So the sum goes outside, we have the variance of xi, which gets to n sigma squared. Okay, because the variance of the xi's were n sigma squared. So putting everything together, we have this bound here, which behaves as 1 over n, but 1 over n goes to 0. And so we have proved the weak law. Okay, understand? Any questions? So pictorially, what is happening? Okay, pictorially, we have the following. I don't want to write this again. Copy, paste here. Okay, pictorially, what's happening is the following. All right, this is exactly equal to cumulative distribution function of Sn over n, expected value of x plus epsilon minus cumulative distribution function of Sn over n, expected value of x minus epsilon. Okay, this part here is Sn over n. What is this event here? How do we get this? Seems very fast. Okay, so here is expectation value of x. Here is expectation value of x plus epsilon. Oh, this one is wrong side. This should be inside here. Okay, all right. Okay, let me explain. What is the event on the left-hand side? That's why I say these notes, there are some small typos, but here definitely correct. Okay, because I'm working this out slowly. Okay, so let's look at this number line here. You have expectation value of x plus minus epsilon here. What is the event on the left-hand side? The event on the left-hand side is the probability that your Sn over n lives inside here, right? Your Sn over n belongs here. Agree? You need to rearrange this a little bit in your head. Because Sn over n deviates from the expectation by less than epsilon. So it must live inside this regime, right? This region here. It must live inside here. Okay. So what is the right-hand side? All right. So the right-hand side, what is the meaning of f of Sn over n? This is the probability that Sn over n is less than equal to expectation value of x plus epsilon. Right? That's the meaning of cumulative. So this guy in the blue, maybe we make it green so that we are very green. Okay. So this is the green guy here is the probability all the way you sweep to the left-hand side up to s expected value of x plus epsilon, right? Now what color do you like? This brown, I guess. Like here, this guy here is all the stuff up to here. You're taking away this part here. So what is the difference? The difference is, maybe you choose this color here. The difference here is nothing but the difference between the green part and the brown part, which is this part here, which coincides on the left-hand side. Agree? Yeah, it's a matter of bookkeeping. Bookkeeping, careful bookkeeping. So now, can we draw the distribution of f of Sn over n as a function? All right, so what's happening here is as follows. When n is pretty large, okay? So here we have the expectation value of x, we have the expectation value of x plus epsilon, we have expectation value of x minus epsilon. So any cumulative distribution function, all right, is always increasing, at least non-decreasing, okay? Be careful. So what's happening here is that, okay, here we are, left-hand side is always like this. Here we are going upwards. My drawing may not be very good. This is going towards 1. Okay. And what is happening here is that, okay, I look at this part and I look at this part here, corresponding to expectation value of x plus epsilon and minus epsilon. And I look at this distance here. In a regular lecture, right, if I don't use this, I don't have so many colors. So here, this is 1 minus delta, very big. When n is large, when n gets large, so this is for some n. When n gets larger and larger, what happens? All right. What happens here is you concentrate. You go, when n becomes even larger, this curve becomes steeper and steeper. Okay. So the probability of actually landing in that interval, what's the probability of landing in that interval here? Okay, it's getting bigger and bigger, as you can see. Here, this length here is going to be bigger than 1 minus delta, right? As n becomes larger, then your cumulative distribution function converges in some sense to a step function at expectation value of x. Okay, so let me repeat. First and foremost, let's consider a moderate n. For a moderate n, you get the red line here. And what is the probability that you land inside this interval? Well, it's nothing but according to this formula, the difference of the cumulative evaluated at expectation value of x plus epsilon here. Maybe I use this color. Here and here, the difference here, that is 1 minus delta, pretty large, okay? But as you can imagine, as n becomes larger, we are going to get a cumulative that is even steeper, concentrating at expectation value of x. And what happens here is that if I evaluate again this length of this interval here, then I get to this point here, this difference here in purple, and I get a bigger probability. I'm not sure how clear this is, but it is very clear in Gallager's book. Okay, so this is the intuition behind weak law. All right. Now, remark. The bound sigma squared over n epsilon squared is extremely loose in practice, as you saw from Haiyun's example of the Bernoulli. Okay. In fact, for random variables x such that the MGF, GXR exists, then we are able to control this much better. Minus expectation value of x bigger than epsilon, less than E. You have already seen this. Hopefully remember, mu x, expectation value of x plus epsilon. So this is by the Chernoff bound, right-sided Chernoff bound. Because this guy here can be decomposed into two parts, right? This is controlled. This is exactly equal to the right-sided part plus the left-sided part. And this is the upper bound. Sorry, wrong pen. This is the upper bound for this right-sided part. Understand? And I'm going to write something now. Plus e to the n mu of the minus x random variable, expected value of x minus epsilon. Okay, there are some there's a small error in my handwritten notes, but I'm sorry, using the wrong pen. Now this part here is the upper bound for this part. So this is the this thing that I just highlighted is the upper bound for this left tail. In the left tail, our random variable is minus x, and we evaluate at this point here. Okay, so these two for symmetric random variables are the same, but in general they need not be the same, so we separate them out. And you have seen that this is negative, so this thing decays exponentially. Okay, so this has this behavior. The behavior of the Chernoff bound is that you have that this is e to the minus n constant bigger than 0. So this decay is exponentially fast, much faster than this polynomially fast thing that is given by Chebyshev. Chernoff is much faster. Decay. Okay. Anyone has any questions? Exponentially fast decay of the tail probability. This is called tail probability in the theory of large deviations. Any questions? People at home, any questions? Where's Vivek? Disappeared. Oh, there's usually a Vivek here. Any questions from the audience here? Or is it super clear? Yeah. Yes, you can think of it exactly. It's a confidence. You are trying to give a confidence interval. In machine learning, this is called peg bounds. Okay. So with probability at least 99%, we are confident that our random variable is in this small little ball. It's in this small little interval. Where's my interval? Here. With probability at least 99%, high probability, then we are confident that our random variable, the empirical average, must be inside this small little ball or small little interval close to the expectation. So this is a sort of probabilistic confidence interval, if you wish. And this has many applications in a variety of studies, especially in the things that I'm doing now, like online learning. Okay. Okay. So now I want to talk to you about my favorite theorem in the world. What's my favorite theorem in the world? The central limit theorem. Okay. Now you see, what's the motivation for the central limit theorem? This is the most useful theorem in the world. Okay, you look at this picture here. What's wrong with this picture? What's useless about this picture? Actually, this picture is pretty useless, you see. Because when n is super large, f of Sn over n, this function here, goes towards a step function, essentially like this. I don't really care where is the solid and the not solid, because you converge to this. You just look at these things that I've drawn here, and you let n tend to infinity, right? You get to this. So this is not informative. Why is this not informative? Because if you give me a random variable, okay, I can only tell you that its limiting distribution or limiting behavior is this. So what's the information that's provided here? Only the expectation, right? You only can deduce expectation from the many, many experiments that you have done. You toss a coin or you toss a dice, many, many times you observe something, you can only tell me expectation here. That motivates us to consider more refined estimates as n becomes large. And that motivates the central limit theorem. So I just want to make some remark here in English. What does f of Sn over n look like when n tends to infinity, when it's large? It is exactly a step function that jumps at the population mean. Okay, so this is not interesting. Okay, now let's consider a different setting. Okay, we have a bunch of random variables, independent and identically distributed, IID, and we consider the following normalization. Zn is equal to 1 over square root n sigma sum I running from 1 to n of xi minus expectation value of x. So now this is slightly, okay, say for simplicity, expectation of value of x is 0, sigma is 1. We can always do this sort of normalization to make our lives easier. Then, okay, rest the remark. Okay, suppose the expectation is 0 and the mean is 1, or the standard deviation is 1. Then how does Zn relate to Sn? Right? So remember what is Sn? Sn is the empiric, Sn is the sum of the NID random variables. Maybe I will do Sn over n is the average of the NID random variables. Right? So these two are intimately related. And in particular, this Zn is bigger by square root n. Right? This Sn over n is the average. Here, what I'm doing is I forget about the sigma and the expectation value of x. Here I am multiplying my average by square root n, essentially. Okay, so I'm making it bigger by this factor square root n, and I'm saying that I will get something interesting. Okay, not I am saying, but central limit theorem says. Okay, now let's just do one simple calculation, and that is what is the expectation value of Zn first. Okay, now if expectation is linear, so we can bring this inside. So we have basically we can bring this expectation inside. Then we have xi minus expectation value of x. Everything is nice and IID. This is 0. Agree? Now we have do variance as well. Now so this is 1 over n sigma squared. Everything inside here is independent. So the sum commutes with the variance. Become like this. Here we have n objects. And each one of these objects is of sigma squared, because I said they are, variance sigma squared, and so this is 1. So we have essentially normalized everything. Okay, by doing this operation here, we have taken away the mean, and we have divided by the standard deviation. So we have created a bunch of IID random variables. Sorry, we have created a sequence of random variables with 0 mean and unit variance, just to make life easier for us. Okay. Just to make life easier for us. Okay, so let us consider, so this is the central limit theorem, favorite theorem. Okay, so we have a sequence of random variables here, xi running from 1 to infinity, IID. So expected value of x is finite, sigma squared finite. Okay, so now you go home and show that if this is finite, it's enough that this is finite. All right, so this is saying too much, using too much saliva already, right? So for all z in R, Okay, so this is the z. This is just some scalar. If I look at the limit of the probability that this normalized sequence of random variables is less than z, so this is the cumulative distribution function of the z, which is created like this. It's a slight rescaling of the empirical average. It's a square root n version, square root n multiplied version of the empirical average. Okay, let's just look at this. Then this goes towards phi of z, which is the Gaussian cumulative, Gaussian CDF. And more precisely, this is integral up to z, 1 over square root 2 pi e to the minus u squared over 2 du. Aha. So what this is saying is that, okay, now let's look at the cumulative distribution function, not of f, not of f of Sn over n. Now I don't want to sketch f of Sn over n, but I sketch f of Sn over square root n, and I plot this. Okay, so this is the z. Assume that zero mean and unit variance. Okay, I plot this. Now let this be very large. Okay, I also want to start at 0, the mean to be at 0. So the central limit theorem says that as Zn becomes large, we converge, the CDF converges to that of a Gaussian. And this is the Gaussian CDF, which is very ugly. It should cut at 0. Okay, so this is equal to 1. This should be half. This should be 0. Sorry, yeah. This is the Gaussian CDF. This is not the Gaussian PDF. The Gaussian PDF is like a bell-shaped thing. Okay, this is the Gaussian CDF. We are accumulating from the left-hand side. So this is the picture when n goes to infinity for this random variable Zn, which is Sn over n, Sn over square root n. So the point here is that if you have a bunch of random variables, you add them up and you normalize by square root n, you never get this jump anymore. Just now we got this jump. You see this thing here? You got this jump. If you normalize by square root n, you get this Gaussian behavior. Quiz question. What if you normalize by Sn over n to the 3 over 4? Do we get this jump? So half is the sweet spot. Huh? Half is like the sweet spot that we get this Gaussian behavior. This quiz question I asked in a few years ago, n to the 3 over 4. Now another quiz question could be, let's say if I normalize by 1 over 4, less than half. What does this random variable look like? Or what does this 3 over 4 thing look like? This one. Oh, go and prove something about it. Okay, so the claim here is that if we normalize by anything that's bigger than half, okay, exercise that I think of on the spot, Sn over n to the half plus gamma, any gamma bigger than 0. This converges to expectation value. No, this converges to something. What is that something? So suppose all the random variables are 0, okay, this converges to 0 in probability. Okay, if I let the gamma be slightly bigger than 0, so I let the thing below be half plus gamma, anything bigger than 0, this goes to 0 if all the random variables have 0 mean. Okay, I think this is true. Conjecture, go and prove it. Now I just think about this on the spot. Most likely true. This is one of my quiz questions, I think, where I let gamma be a specific 1/4. Okay, so in this case here, forget about this. Most likely I'm correct. Okay, for in this case here, in the central limit theorem, okay, what's happening here is that we can say that Zn converges to a Gaussian with 0 mean and variance 1 in distribution. We say that Zn converges to a standard Gaussian in distribution. So notice that convergence in distribution really involves the convergence of the cumulative distribution function. Okay, this object here is the cumulative distribution function. It's crucial. Okay, convergence in probability, and I'll repeat all this later on, involves the convergence of this sequence of numbers. The probability of this sequence, the sequence of numbers converging to 0. This thing here is a sequence of numbers. You plug a certain sequence of events inside the probability. You get a sequence of numbers. Convergence in probability is assessing whether this sequence of numbers goes to 0 or not. Now, convergence in distribution, however, involves this entire function, which is the CDF of an appropriately scaled sequence of random variables Zn. We are asking whether this sequence of functions goes to Gaussian CDF or not. Okay, this is central limit theorem. It's a statement about CDFs. Okay. All right. So this is the central limit theorem. And in an introductory probability course, you would have used that central limit theorem to calculate some probabilities. Like what is the chance that this deviates from that? And you're not going to do that sort of calculation. So to prove the central limit theorem would be too much for us. Okay, but I want to show you a rough proof of the central limit theorem. Proof sketch of CLT using transforms, using MGFs. So we will assume the simple case where we normalize everything. Okay, otherwise I need to carry a lot of things around. So let's consider the cumulative distribution, the moment generating function of the random variable of interest. Okay, so this is the moment generating function. Let's say R is some real number. Okay, so I'm just going to do a rough thing. Okay, so don't blame me for being imprecise here. So this is the 1 over square root n normalization of these random variables, right? 1 over n normalization. So what we have here is, okay, oh, the R is missing, this R here. Okay, so we have that this is gx of R over square root n raised to the power of n. Now, this is too fast. If you are going to be a professor, this is too fast to teach your students. So we need to substantiate this step a little bit. So what is this? This is expectation value of e to the R over square root n, okay, of x. Okay, is there something wrong? Yes, this n here comes from the fact that we have a product. Okay, this here comes from the fact that all these guys are ID. So we can rewrite this. Let's do this slowly. We can rewrite this one additional step here. This is equal to product up to n of I running from 1 e to the R over square root n xi. This becomes product I running from 1 to n of the moment generating function e over square root n xi. And this is exactly equal to that. Because all the xi's are identically distributed. Now this is clear, right? Right? So this guy here, because of the sum is in the exponent, becomes a product normally. Independence is used here to bring the product outside. But each one of these terms here is equal to the g with the appropriate scalings R over square root n here. Understand? Now we are in business. Because I don't like to take things in the exponential domain. I want to take 1 over n log e to the R Zn. That becomes 1 over n log gx R over square root n. Here we get the what Gallager calls the semi-invariant MGF. In fact, just now my student Haiyun said this, right? But nowhere else in the world do they call this semi-invariant MGF except in this book. This is called the cumulant generating function in Wikipedia. I always use cumulant generating function. And cumulant generating function is better Because if you continually differentiate the log of the moment generating function, you get the cumulants of the random variable. Go and find out what are cumulants. Okay? So you have this. Now, at this point in time, okay, what we have is the following. Let's consider this function here, r over square root n. Now, we are able to do, say we are able to do Taylor series expansion. Okay, gx prime of 0 r over square root n plus gx double prime of 0 over 2 r squared over n. Okay, say we truncate this and forget about all these terms here. Okay, what is gx of 0? What is gx of 0? Gx of 0 is nothing but 1. Okay, what is gx prime of 0? That's the expectation, right? Gx prime of 0 is exactly the expectation. So this guy disappears beautifully. Gx double prime is the second moment, which is equal to the variance, which is equal to 1. So this is plus half, correct or not? Half of r squared over n. Okay. Yeah. So now so this is equal approximately. Okay. So now let's go to plug this guy here back into here. Okay. So we have maybe we just ignore this for the moment. Log of expectation value of e to the r zn equals to log 1 plus half r squared over n. Okay. Now when n is very large, log, okay, when epsilon is very small, this is about epsilon. Okay, this is some fact. Okay, so this is about r squared over 2n. Oh, right? This is some analysis thing. Okay, so now let's plug this back into this, here. All right, so what we have is expectation value of e to the r zn. Expectation value r zn. Let's plug the g thing here. You have e to the r squared over 2n. Because I've only dealt with the log here, I need to get back to the e domain. Then I need to take a power n. This is approximate also. So I basically just approximated this guy here as n becomes large. I approximated this guy here. Now then you see that actually man or God made the earth so beautiful that this n and this n cancel. All right, so we have n random, this n outside here, this n random variables comes from here. This square root n allows us to use Taylor to get this part here. All right, so this n and this n cancel beautifully. This is like law of physics. Everything turns out to be so beautiful. This is e to the r squared over 2. Which, if you know about moment generating functions, this is the MGF of a standard normal Gaussian. This is the very rough proof of the central limit theorem. There are a lot of steps in between that are very rough. So this is not a terribly good proof, but this is the big idea of the very precise proofs. Any questions? Please don't ask me questions like, oh, why is this approximately? Because I didn't do this carefully, okay? Any questions about this? This is only proof sketch, okay? Now, this is equal to 0. I just want to make clear, because expectation x is equal to 0. So this guy here is equal to expectation x. Now this guy here is going to be expectation value x squared, which is equal to 1. Understand? Oh, too fast? Actually, it's too fast, it's okay. You can go back and listen to me again. Right, so this gx double prime 0 is equal to expectation value of x squared is equal to 1. Okay, so this term in the middle here disappears. You're left with this one, which is 1. Please know why it is 1. And then you're left with this term here, which is 1 over 2, r squared over n. Now this guy here, I don't even need to take logs here. I don't even know why I took log here. Never mind. We just work with this G. Then, oh, I take log because we want to use this identity that log 1 plus epsilon is about epsilon. But if you're also convenient, you also know you can work in the E domain. I just like to use this inequality here, or this approximation. Okay, then we basically plug, this is the gx of r over square root n inside here, and the n's magically cancel, and we get the MGF of a standard Gaussian. We're actually lacking one more theorem here. We are lacking the theorem that if the MGF converges to that of a Gaussian, the cumulative distribution function converges as well. Okay, so we have that MGF converges. MGF of Zn converges to MGF of a standard Gaussian pointwise. So for every R, this happens. Now, this implies actually that f of Zn of Z converges to the phi of Z Gaussian cumulative for every Z in R. This implication here is far from easy. This is called Levy's continuity theorem. So So I've only proved up to the use of Levy's continuity theorem. This one you don't need to know. You don't need to know the proof of the central limit theorem either. Okay, but I just show you a proof sketch to make sure you understand this is believable. Okay? Yeah. Any questions? This Levy is actually like this. Okay. There are some strengthenings of Levy's continuity theorem. In some of my papers, I improve on this. Last time, long time ago. Yeah. We improve on this slightly. We don't need pointwise here. We don't need this pointwise. This is too strong. Okay, so this is Levy's this is central limit theorem, rough proof. Okay, I still have a few other concepts to go through. So we have talked about Wick law. We have talked about central limit theorem. Okay. Now I want to talk about general convergence in distributions. Now, just now I talked about the fact that, okay, if you have a normalized, recall, if I have a normalized sum of IID random variables, actually you don't even need IID random variables. Then this converges in distribution to a standard Gaussian if you have the correct statistics. Otherwise, you need to do normalization. Okay, this is the central limit theorem. Now, more generally, let us define the notion of convergence in distribution. This is convergence in distribution for a normalized sum of ID random variables. Okay, but more generally, definition: a sequence of random variables Z1, Zi, I running from 1 to infinity, is said to converge in distribution to a limiting random variable Z if limit n tends to infinity of the cumulative distribution function of the random variables in question. Maybe I make this consistent and talk about n. Okay, is equal to the cumulative distribution function of the limiting distribution. But with a caveat that you don't really need to care about. For all points of continuity of FZZ, for all points Z of continuity. So if FZZ is not continuous at some Z0, we don't need to care about this statement. All right. But if FZZ is continuous at this Z, we care about this statement. Yeah, we use this definition. So this is the notion of converge in distribution. Okay. So note that we don't really always have to converge to a Gaussian. All right. If this sequence of random variables is very bizarre, we could converge to other distributions. We don't necessarily have to converge to Gaussian. In much of my work, we converge to chi-squared, which is also very important. Okay? We like to converge to other things as well. All right, so, but since we know the CLT, an implication of the CLT is that the central limit theorem is that if I define this sequence of random variables, where the constituent random variables themselves are IID, so the xi's are IID, so I can just talk about this. I take away the mean, I divide by the standard deviation. So I created this new sequence of random variables that is indexed by n, is the suitably normalized sequence of random variables, okay? Then Zn converges to Gaussian in distribution. Okay, understood? So now I'm going to talk about a sequence of convergences. I'm going to talk about sequence of convergences. The first convergence is the notion of convergence in distribution. Convergence in distribution is the weakest form of convergence. You are going to prove in the homework that I'm going to give you the solution, since I'm so nice, that convergence in probability implies convergence in distribution. It's a 3-line proof. Okay, so the next thing I'm going to talk about is convergence in probability. Slightly stronger. Any questions about this statement here? This CLT part we have already proved, or semi-proved, through the use of transforms, through the use of MGF. But a proof of CLT requires a little bit more, like Levy's continuity theorem. Yeah, sure. Sorry, not enough board space.
Just to confirm, right?
And
Write it down.
yeah.
Require your xi to be IID.
Yes and no. Yes and no. Yeah, here, of course, if xi is IID, we have this. We don't really need xi to be IID. Yeah, my proof requires IID. Without IID, it still holds, okay? But under some conditions, all right? What condition is that called? Lindenberg condition. Go and Wikipedia it, okay? Under Lindenberg's condition, we have CLT. In particular, we don't need identically distributed. That is, you see, the important thing in this proof, what is the important thing in this proof here? The important thing is to get to here. Here requires independence. All right? Here, this step here requires independence to move the product outside. This is super crucial. But it's not so crucial that all these are the same. It's not so crucial that all these are the same to be able to collect it into here. Right? It could be different. Then I just have to take another limit somewhere. So independence is important. Identical distributed is not important. We can easily generalize this to non-identically distributed. But for the sake of simplicity here, IID, we have this simple statement here. Okay, any questions? Oh, same. It's about the same. Yeah. And it's not quite the same. Can you go and find out what's the difference? One is for real, one is for complex, I think. I even have a stronger generalization in my paper. Okay. Oh, okay. So this is the first form of convergence, the weakest form, convergence in distribution. What do I want to talk about next? Definition. A sequence of random variables, Zn. Let's change everything to Zn. Converges in probability. Okay, this concept is also quite not so difficult. There's going to be more difficult concepts. Probability to a limiting random variable Z if for every epsilon bigger than 0, no matter how small. If I look at the sequence of numbers given by the probability that Zn deviates from its limit by more than epsilon, I look at this sequence of, this is nothing but a sequence of numbers. This sequence of numbers has a limit and the limit is 0. Okay? So, for example, the normalized sum of IID random variables, again, we don't need identical distributedness. Independence is more important. Then you may ask me, right? Is independence really important? What if the random variables are Markov? There's also a Markov central limit theorem. There's also a Markov weak law. no problem. As you can imagine, all these things, you can write multiple papers on it to sustain yourself through a 60-year career, right? Every year you write something different. Right, so, okay, but what do I want to say? Okay, if this is the sum of IID random variables, okay, IID simple, all right, then this converges in probability. We have already shown this to, what does it converge to? Expectation value of x as n tends to infinity. Okay, assuming finite variance. Okay, now you may wonder, right? Here the definition is converges in probability to z. Z is a random variable. Here, this example, this sequence of random variables which I treat to be my Zn seems to converge. Hey, this is not a random variable, it's a number, right? What's happening? But this number here is a special case of a random variable. It's a degenerate random variable. What we are saying here is that this sequence of random variables converges in probability to this degenerate random variable, which is nothing but a random variable that takes on the probability 1 at expectation value of x and 0 elsewhere. Okay, so it's a degenerate random variable. You can still converge to a number, all right? You just replace, if this is a number, you replace this in this definition by a number, okay? So that's the meaning of convergence in probability. Convergence in probability means that you're assessing this sequence of numbers for every epsilon. Okay, we will do a few examples soon. Okay, fact, homework. When I give you this sort of homework problems, right, I don't leave you in the lurch because I'm a nice person. I give you copious amounts of hints to help you to do this sort of things. Okay, fact, convergence in probability implies convergence in distribution. So for this sort of fact that you have to prove, right, you need to know the definitions. You need to know what to prove. All right. So here you go home and do. I already gave you one hint. Okay. All right. So this fact, homework, and I will provide the solution. There are two other definitions of convergence that we care about. The next one is also not very difficult, but it's a very strong form of convergence. All right, it's LP convergence, but I'm only going to talk about L2. All right, so a sequence of random variables, so I don't write so much. Definition. A sequence of random variables, converges in mean squared. Converges in mean square to z. So this is the definition. Converges in mean square to z if, now I'm not looking at the probability anymore. I'm looking at the mean square. So I take z n minus z square equals to 0. Again, I'm assessing the convergence of a sequence of numbers. This sequence of numbers is the expectation of the deviation of Zn from its limit, take the square. Okay, so this expectation is nothing but a sequence of numbers. And I'm assessing whether this limit is equal to 0 or not. Or this limit cannot be negative because the expectation here is that of a non-negative random variable. So we are asking whether the limit is 0 or not. Okay? So here's a simple fact that I will prove for you. Sn over n, or Sn in my lectures is always x1 run up to xn, okay? Sn is always x1, xn. Say all these are, xi's are also IID, okay? Converges to expectation value of x in mean squared. All right, so let's prove this. This one I will prove for you. Not so difficult. Difficult one you do, all right? So what we did prove just now is that this converges to, this sequence of random variables converges to the expectation in probability. Now we're going to prove convergence in mean squared, okay? So we just need to track the definition, right? So this is now our Zn. This is our Zn equals to this. We just need to track the definition. So proof, okay? Let's form expectation value of Sn over n minus its perceived limit, which is expectation value of x. And let's square that. Okay, so we just need to calculate this. How to calculate this is a matter of whether you are careful in bookkeeping or not. Okay, let's see whether I am careful in bookkeeping or not. Okay, let's see. Now, hopefully I can do this bookkeeping. Oh, you see, this guy here is the mean of this guy here, right? Let's calculate. Let's do an auxiliary calculation, Sn over n. This is 1 over n of expectation value of this guy here. Right? But each one of these guys here has expectation value of x. So this is expectation value of x. Right? So this random variable inside here, maybe this color here. This random variable inside here has 0 mean. You agree? This green thing has 0 mean. So this is the second moment of a random variable with 0 mean. I already said that if you have a random variable with 0 mean, then the second moment is equal to the variance of that random variable as n over n. Right? So, correct? Yes, okay. So now let's continue. Variance of Sn over n. This is 1 over n squared. Variance of, so Sn is equal to this. Right? So I'm not cheating. Right? This is exactly Sn. Right? Cool. So now all these people here are independent. So we have 1 over n squared, the sum of the variances of xi. But you notice that all these are sigma squared and sigma squared. Oh, this one, you need the sigma squared finite. Okay, otherwise something is going to blow up. So no matter what, you will have sigma squared over n, which converges to 0. Okay, so this guy here converges to 0, which is a proof that Sn over n converges to expectation value of x in mean squared, if this is true. Okay, so this is a simple calculation. These sort of things you should know how to do. So it is true that mean squared convergence implies convergence in probability. This requires a more difficult proof that I didn't ask you to do. Okay, but I'm going to draw a picture later on of the implications. Okay. Now we save the best for last. Oh, before we save the best for last, are there any questions on this calculation? People at home, do you have any questions on this calculation? Can you see me? Any questions? You can type the questions here. Any questions here? Can, right? This sort of independence thing. Oh, by the way, right? We don't really need independence. We can have uncorrelatedness, right? Because uncorrelatedness is enough for this variance to decompose into the sum of the variances. In fact, we could have little bit of correlation as well, right? Because this is n squared here. This is only order n. So we could still have a little bit of correlation. So this in some applications is useful. For example, if the xi's are Markov, so there's a little bit of correlation, then we can still show convergence in mean squared. We are trying to squeeze as much juice as possible out of this statement. This 1 over n is too much, right? We can still do a lot of things and write a lot of papers. Okay, any questions on this calculation? All right. As I said, we are going to save the best for last. So, okay, there are four modes of convergence you need to know. What have we done? Convergence in distribution, in probability, in mean squared. I think these are relatively okay. Right, so now we have the following. We have Zn, a sequence of random variables. This is a definition. Converges to a limiting random variable, Z, with probability 1. also called converges to Z almost surely if, now I look at the probability of, okay, the following event. Probabilities are always of events, so I'm looking at subsets of the sample space. Omega in omega. I'm looking at all those omegas in the omega, big omega, for which the following happens. If I look at the limit of this sequence of functions, okay, and I look at whether or not it agrees with the limiting random variable, this is equal to 1. So the places in which the omega, the places in which this limit does not equal to the limiting random variable has probability 0. That is another way of saying converges to a limiting random variable with probability 1. Now this is, to me, the first time I saw this, I didn't get it. The second time I saw this in another course, I still didn't get it. Maybe about 10 years later, I got this. You really need to live with this. Okay? So this is the, I don't know whether you have seen this before, but this, to most people, maybe this is the first time seeing it. I hope that the first time you are seeing this, you will get more out of this definition than the first time I saw this. So I'm going to give you some examples and some illustrations. Okay? But before that, let me continue talking a little bit. We write this as Zn converges to Z almost surely, or Zn converges to Z with probability 1. Okay? Now, oftentimes, I'll ask you to check whether a sequence of random variables converges to some other limiting random variable in probability, in distribution, or almost surely. So, to check almost surely, this definition is completely useless. It's almost completely useless. You cannot use this to check. But what you can use to check is the following fact that I prove in the notes that you don't need to know. Zn converges to Z almost surely, which is defined above, or with probability 1, if for every epsilon bigger than 0, I look at the following probability. Okay, Zn minus Z less than epsilon for all n bigger than or equal to m. So this is a sequence of numbers in m. Okay, now I'm fixing m. And I'm looking at this guy here. I'm looking at this guy and asking whether this is true for all n that is bigger than my m. Right? M is fixed. I'm looking at this statement for all n bigger than a certain m. So let's draw a picture here. This is m. I'm asking the question, okay, is this statement true for m plus 1, for m plus 2? So this is my n. My n's live here. Understand? So I need to check this, check this, check this, m plus 3 all the way. So this guy here is a sequence in m. You can think of it as am. Okay? Now, a sequence of random variables converges to a limiting random variable almost surely if I look at this limit, I take m going to infinity, this is equal to 1. This is a check. Now, it's not obvious that this definition is the same as that definition, but it is. I proved it in the notes. You don't need to know. You just need to know how to use this. Okay? There are some other checks that you can do. Some of them you may have come across. Borel-Cantelli lemma. But we don't need to know this for the purposes of the rest of the course. And this check is very convenient, as I will show. Okay? So I just want to make a remark, all right, saying the following. Remark. Convergence with probability 1, also called almost surely, okay, means that the set of sample paths omega in omega that Zn converges to the limit Z omega in the sense of a sequence of numbers converging to a limit converging to a limit which is another number, because these are now numbers. If I fix the omega, these are now numbers. I can then talk about convergence of numbers, which I started talking about at the very beginning of my part of this lecture, has probability 1. This is just a restatement of convergence in probability. I'm going to tell you more stories later on, tell you very beautiful stories later on, because all this is maybe a bit abstract, maybe very abstract, okay? But I want to do one example for you to show you the difference between convergence in probability and convergence almost surely. Now, the thing that people get confused about is with improbability and with probability 1. Convergence in probability involves convergence of this, okay? Convergence of this sequence of numbers. Just a convergence of sequence of numbers. Convergence almost surely requires us to check this event, whether this event has probability 1 or not. The other two, I think, are simpler, because the other two, convergence in distribution, you're checking the cumulative distribution function, which is a completely different object. Convergence in mean squared, you're also checking just this expectation. You're checking this expectation. So it's very easy to differentiate between convergence in mean squared, convergence in distribution, but the other two are a bit closer, at least in my brain. So I want to make it clear to you what's the difference in convergence in probability and convergence with probability 1. Okay, and I will do one example, then I will provide more intuition. Okay, so let's consider this example. Okay, example. Let us consider this sequence of random variables xn taking on the values 0 and 1. All right, with probability 1 minus 1 over n, and with probability 1 over n. And the xn's are independent. Now, clearly, they are not identically distributed. All right, so we don't need to talk about identically distributed. They are clearly differently distributed, but they are independent across the n. Okay, the claim is the following. This sequence converges to 0 in probability. That's claim 1. And claim 2, xn does not converge to 0 almost surely, or with probability 1. So we'll prove these two things. Okay. All right. So the proof of the first one should not be too difficult. We just need to check something. All right. So, maybe why don't we be more ambitious and we do 3 things? Because this is the third thing. Okay. This is the second thing. Xn converges to 0 in mean squared. Let's do 3 things. I realized that I had this one, and I think I didn't do probability in the notes, right? Maybe I did. Yeah. Okay. So anyway, I did 3 things. Let's prove all these 3. I don't think that takes that long. Okay. Proof of 1. How to prove that this converges to 0? Okay, so what we need to do is we need to assess the difference between this and 0. Okay? Assess this. Okay? So suppose we take epsilon between 0 and 1. Then what's the chance that xn minus 0, which is nothing but the absolute value of xn, is bigger than epsilon? That is exactly the probability that xn is equal to 1. Right? If xn exceeds 0 by epsilon, it must be 1. No other choice. But this is exactly 1 over n. And this goes to 0. That means that by the definition of convergence in probability, we have that xn converges to 0 in probability as desired. Okay? Any questions? So we're just tracking the definition. That's the definition of convergence in probability. Xn converges to a constant in probability. Right? We're just tracking the definition. So here, from here to here, we have that, this is 0. This is minus epsilon, epsilon. What is the percent? This minus 1, 1 here. So xn can only take on two values, right? It can only take on values 0 and 1. So if we are not in this, if we are not here, we must be here. So we are identifying this point here. This is basically the probability of xn bigger than epsilon is exactly xn equals to 1, right? Which by definition is 1 by n goes to 0. Okay. All right. Now let's do any questions? We are going to do the mean squared one, which I don't think is that difficult. Okay. So for mean squared, we need to check the following, right? We just need to check this, whether this guy goes to 0 or not, right? But this is exactly equal to expectation value of xn. Why? Okay, first and foremost, you can get rid of the 0, okay? It's an eyesore. But xn can only take on two values, 0 or 1. Now, if it is 0, 0 square is equal to 0. 1 square is also equal to 1. So 0 and 1 are the only numbers for which if you square them, they remain the same. So I square the xn, it remains the same. Okay? Because the xn only takes on 0 and 1. So lucky, right? So now let's calculate the expectation value of this guy here. So you take this number multiplied by this number, and this number multiplied by this number, right? You add them up. So this again 1 over n. You get 0 multiplied by 1 minus 1 over n plus 1 multiplied by 1 over n, which is 1 over n, which goes to 0. So we have that by the definition of convergence in mean squared, xn converges to 0 in mean squared. Okay? Anyone has any questions on the calculation? Very good. Following me, the next calculation is going to be a little bit interesting. These calculations are quite easy, tracking the definitions. Okay. All right. So now let's do let's prove this claim that xn does not converge to 0 almost surely. So part 3. All right. So let's calculate. So what do I have to check? I have to check this guy here. Okay. So now let's cut this. Let's look at this. So I want to be able to check this guy here. But now my Zn is actually xn. I just call it a different name. I call it xn 0 here. Let me check this sequence. Let's call this sequence AM. It's a sequence in M. Right? It's a sequence in M. So I'm going to check this, okay? Now, all these guys are independent. Okay? So I'm going to choose epsilon small. So I'm going to write AM. All these guys are independent. Okay? So what I have here is that AM, which is this probability, is the probability, that xn is equal to 0 for all n bigger than or equal to m. If I choose epsilon small, like 0.1, then what is the probability that xn is less than epsilon in absolute value? It must be 0, right? Because the other choice of xn is 1, very far away. So xn must be equal to 0. This is the first fact, okay? Okay. So this means that, okay, I'm going to do this slowly. We have probability xn equals to 0, xm equals to 0, xm plus 1 equals to 0. For all n bigger than m, right? X m plus 2 equals to 0 all the way. As I already drew for you just now, is the number line. Here is our distinguished m. I need to check this guy at this point at m plus 1, at m plus 2, and so on and so forth, right? So that's exactly what I'm doing. This is what I'm checking, okay? But all these people are independent. All these random variables are independent. So this becomes product of n equals to m to infinity, probability xn equals to 0. Agree? All the guys are independent. Okay, so this becomes product n running from, as I said, this is a bit difficult. Okay, 1 minus 1 over n by the definition. All right, you take on 0 with probability this amount. 1 minus 1 over n. This is the definition of our random variable, right? Okay, so our job is to evaluate this guy here. So there's a formal way of doing this and there's an informal way of doing this. So let's do the informal way. So this is going to be a telescoping thing. Okay, over n minus 1. Let's write it this way first. This is going to be telescoping. Okay, so let's write this out carefully. The first one is m minus 1 over m. The second term is m plus, so m over m plus 1. M plus 2, m plus 1. Dot, dot, dot. Do you see the pattern? So after you see the pattern, you see that this can cancel this. Oh, sorry. Oh, there's something missing. Oh no. Did I make a mistake? No. Okay, you cannot do this. Sorry. Okay. Yeah, it's better to add limits here. I do too fast. Okay. So let's go to this k, limit k to infinity. Okay. Okay, sorry about that. But this is say limit k to infinity. You replace the upper one by k. All right. And let's write this out in detail. Limit k to infinity, n running from m to k. So the top limit is actually infinity, and n minus 1. Okay, now let's do this calculation again, slowly. Okay, so we have limit k going to infinity of, let's write this out carefully. All right, so the first person is m minus 1 over m. Right, the second person is, what's the second person? M plus 1 at the bottom, m at the top. M plus 2 at the bottom, m plus 1. Now you see the pattern? Agree? Okay. So what is the last term? The last term is k minus 1 over k. Right, so now let's cancel the things. Slowly. This cancels with this cancels with this cancels with this. And what do we have? This cancels with this. Right? So when all is said and done, we have limit k going to infinity of m minus 1 over k. Right? We have to be a bit careful here. We cannot anyhow do things. This is equal to 0 for every fixed m. Right? That's the definition of the infinite product. You need to take the infinity up there. You cannot be so cavalier as I did. So this sequence, the punchline is that this sequence AM, which is equal to this, copy, paste here, is equal to 0 for every m. Right? I just did a calculation. One more time. This calculation is a bit tricky. So this AM. It's the infinite product. If this is equal to this. Okay? So it's an infinite product up to k of all these guys here. But each one of these guys has this probability. Okay? So this is just clearing these fractions to make it look nice. Nothing much here. So for every fixed k, let me write down this product carefully. The first term is m minus 1 over m here. The second term, you increment this counter, you get m over m plus 1. The third term is m plus 1 over m plus 2. And the last one is k minus 1 over k. And you cancel, and cancel. You cancel this guy here also. You're left with m minus 1 over k, right? Which is here. And you let k go to infinity. For every fixed m, you get this 0, right? So this sequence here is always 0 for every fixed m natural number. What do we have to check? Maybe we forgot. We have to check that this is equal to 1. So now let me take limit m go to infinity of am. But each element of this sequence is equal to 0. So this is equal to 0, which is not equal to 1. So we have no convergence to 0. Okay? We have no convergence to 0. So yeah, this example took a little bit of time, but it's okay. Understood. Any questions? So we always have the following relation. Almost sure convergence, convergence with probability 1. This is a bunch of theorems. Implies convergence in probability, implies convergence in distribution. Here, homework. This is possible. L2, or maybe we call it mean squared convergence, implies convergence in probability as well. The rest of the other arrows do not hold in general. So all we have, how many theorems? 1, 2, there are 3 theorems here that one can prove. And what you will do one of them. Actually, this one is also not very difficult. Okay, so I want to show, okay, any questions about this calculation here?
How do you make sense of the result?
I'm going to tell you soon.
Is it not weird? It is within extreme case.
Yeah, these are some just pathological things that we have to take care of. It's very hard how to make sense. I don't even know how to make sense of this. Yeah. Okay, there's actually a second way of proving this, which doesn't answer your question, unfortunately. You can use a second Borel-Cantelli lemma to prove this as well, because you have independence here. This doesn't answer your question. I don't know how this makes sense. Okay, this is just an example to show you that if you converge in probability, you don't necessarily converge almost surely. You cannot go backwards here. Okay. Sorry, I cannot answer that question. But I want to show you something else that maybe can help answer this question. Okay. So what's the intuition behind convergence in probability and convergence almost surely? So what am I doing here? All right. I basically did simulation this afternoon to try to explain this to you. Okay. So what am I doing here is, okay, I'm creating these random variables, xn equals to 1 and minus 1 with probability half. And I'm creating this random variable I running from 1 to n. I create this random variable. Okay. So here, what I'm plotting is Sn over n. Intuitively, it should go towards 0, right? Intuitively, it goes towards 0, definitely. Because we have these random variables have finite variance, no problem. So what is convergence almost surely trying to tell us? Okay. So this is one sample path, one simulation. So convergence almost surely means the following, right? That Sn minus 0. Okay, I have the limit inside. Limit n going to infinity of Sn equals to 0 equals to 1. That's the statement. What that is saying is that if I choose this epsilon, this is 2 epsilon, all right? The epsilon is shown to be 0.05. Then the chance that I escape this window. All right, so I escape this window here and here only, right? I'm escaping this window. The chance that I escape this window here, all right, only happens finitely often. The number of times the sample path Sn over, oh, sorry, this is Sn over n. The number of times Sn over n escapes or exceeds, let me read this one, exceeds epsilon happens finitely often. Okay, for every realization of the stochastic process. So as you can see here, it only happens finitely often here. You're only exceeding here and here. After that, you are staying inside the window. Okay. Now, convergence in probability is a different animal altogether. What do we have? We are assessing the following: Sn over n minus 0 exceeding epsilon. This equals to this limit here equals to 0. We are assessing this. So in particular, what are we doing? We are saying the following. Suppose we generate multiple experiments. That represents the probability here. Suppose we generate multiple stochastic processes here. Multiple runs. Here I chose 100 runs. Okay? What I'm trying to say here is what convergence in probability or the Wick law is saying is that I look at a large enough n here. This is my n that I look at large enough. The fraction of sample paths that escape my window, the fraction of sample paths, the fraction of experiments that exceed plus minus epsilon is small. As you can see here, if I fix this n to be this, right? I have 100 sample paths here. Trust me, there are 100 lines here. How many of them escape? Oh, I can see a couple here. Maybe here still escape a little. But 3 out of 100 escape. Okay? If I move the n a little bit further to the right-hand side, the fraction that escape will be smaller. So convergence probability is about multiple sample paths. This is about every single sample path only exceeds the this window here finitely often. Okay. All right. So this is some illustration of the difference between convergence almost surely and convergence in probability. All right. So I don't want to draw this picture, so I just MATLAB this picture. Okay. You want to listen to another story? We don't have too much time. I want to take up like 10 minutes more of your time. This story is very interesting. All right. It again illustrates the difference between convergence in probability and convergence almost surely. Every year I talk about this, and every year people are confused. But at least it gives you some further insight about convergence in probability and convergence almost surely. Example, or maybe an analog, it's not an example, analog of convergence in probability and convergence almost surely. We have a committee of 100 people, members. Each member is represented by an omega in omega. We have a committee of people to decide on some important matter. Like 100 senators, right? There's 100 senators, 2 from each state. We call one meeting every day. One meeting of the committee involving the committee every day of the year. This is taken from Quora. Okay, this is not my example. I think it's a good example. Every day, there's a meeting of the committee members. One every day throughout the year. Okay, we are interested in the attendance. So some committee members may fall sick. Some committee members don't like other committee members and so don't want to come. We are interested in the attendance of the committee members. Okay, so let's consider convergence almost surely. This implies that almost all members have perfect attendance over the 365 days. Okay, so the picture is as follows, all right? So we have this. These are the members, and these are the meetings. 1, 2, 3, 364, 365. Members, we have 1, 2, 3, all the way until 99 and 100. So convergence almost surely is analogous to the fact that almost all members have perfect attendance over the 365 days. So for example, this guy has perfect attendance. I'll indicate him by P. This guy has perfect attendance. Perfect, huh? This guy has perfect attendance also. Almost all, maybe only this guy, number 50, has not perfect attendance. Maybe he didn't come here, absent. The rest have perfect attendance. Okay, only one guy, or maybe let's make it more exciting. Let's make it two guys have. Okay, so the rest are all perfect. Perfect, all perfect. All right, and this is also perfect here, but absent here. Absent here and absent here. Okay, so almost all members have perfect attendance over the 365 days. So what this means is that, okay, if we look in the probability world, you look at the size or the probability measure, or the probability of the members such that limit xn omega equals to x omega, this is equal to 1. Okay, so I'm looking at these guys here. Who has perfect attendance? Okay, maybe only a few don't have. That few will turn out to be the missing ones here. The missing ones inside this, but they have 0 probability. Okay, you imagine that they have 0 probability. Okay, now, what is the meaning of convergence? What is the analog of convergence in probability? Well, that means that all meetings were almost all full. Okay, so now let's redraw this diagram here. Okay, all meetings were almost all full. So what is the picture we want to have? Okay, let me see whether I can do this. So for example, this particular meeting, one person was absent. This person was absent. This meeting here, this person was absent. This meeting, this person was absent. This meeting, this person was absent, and so on and so forth. So almost all meetings were almost all full. Okay, so maybe there's someone missing here, absent and absent. All right, so this is indicating that the set of elements omega omega for which xn omega is almost x omega has probability approaching 1. Now, note that if all meetings were nearly full, it may not be the case that any member has perfect attendance. So for this particular example that I've just drawn, none of the members have perfect attendance. The way I've drawn it, okay? So every member is missing on at least one occasion. Okay, so this guy is missing here, this guy is missing here, this guy is missing here, this guy is missing here. Okay, let me move this a little. So we are always missing some people. Every meeting is missing some people. None of the guys have perfect attendance. All right, because convergence in probability does not imply convergence almost surely. Okay. Right, this picture is not very well drawn, but I hope you get to see the picture. Note that if all meetings were nearly full, it may not be the case that any member has perfect attendance. Okay, but if almost all members have perfect attendance over the 365 days, then it must be true that all meetings are almost fully attended, as you can see here. So this is the difference, in essence, between convergence in probability and convergence almost surely. This is one other example for you. Just now that sample path example, I think is more precise mathematically. Don't ask me too many questions about this. This is just some illustration, analog. Yanke asks, why does, let me answer Yanke's question for me. Because AM Yanke, because AM is this quantity here, okay? There are an infinite number of random variables here. Infinite number of random variables. Each one of them is IID. No, each one of them is independent. So we have to write it like this. We can put infinity here, but when we put infinity here, it really means that we are taking the limit of k going to infinity of this k here. All right. When we write this ai I running from 1 to infinity, this is formally k running from infinity of product ai. Similarly, when we write sum running from 1 to infinity, we really mean the following. K of ai. Okay, we have to do this. So hopefully, Yanke, I answer your question. Okay, so this is some formal meaning of the infinite product and infinite sum. Okay, yeah. This is true if the limit exists. Sometimes this may not converge, or there's only lim sub lim infer, no limit. So we have to be careful. If the limit exists, we write it like this. Okay, but here, yeah, you can read my notes to see if this helps in your understanding. But really, you need to work out some examples like this sort of examples to fully understand the difference between convergence almost surely and convergence in probability. And that brings me to the end of today's lecture. And I will see you next week. Next week, we'll start on Poisson processes, which is very exciting. Okay? And you have to prepare for the quiz. I will release all the solutions. Can? Okay. Thank you very much and have a great weekend. Sure, you can ask one slow question also.
So I'm just wondering, convergence in
let me stop this recording first. Stop this completely.